On August 25th, 2012, a spacecraft that had been flying for 35 years crossed a boundary no human-made object had ever reached before, and what it found on the other side broke almost every prediction scientists had made about what that crossing would actually look like. NASA expected a gradual transition, a slow fade from one environment to another, like a river slowly widening into the sea. What Voyager 1 actually measured was closer to slamming into a wall, particles moving at speeds approaching a meaningful fraction of the speed of light, generating temperatures scientists still describe using language that sounds more like a description of a star than the edge of empty space. And that was only the first surprise. The second one involved something even stranger, a fundamental assumption about how our entire solar system relates to the galaxy surrounding it, an assumption that turned out to be flatly wrong. This is the real story of what NASA genuinely did not expect Voyager 1 to find at the true edge of our solar system, and why scientists are still working through the implications more than a decade later. I'm your host, and this is your channel. If you want the real science behind the biggest surprises coming out of deep space, subscribe now because we're just getting started. To understand exactly how surprising this discovery actually was, you first need to understand what scientists thought they already knew about the heliopause before Voyager 1 ever got there. The heliopause is the boundary marking the true edge of our solar system, the point where the sun's constant outward stream of charged particles, called the solar wind, finally loses its ability to push back against the pressure of the interstellar medium, the thin plasma filling the space between star systems throughout our galaxy. Inside that boundary sits everything humanity has ever called home. Every planet, every moon, every spacecraft we've ever launched. Outside it lies something scientists had only ever been able to study indirectly, from the comfortable safety of a solar system they'd never physically left. For decades before Voyager 1 actually crossed that line, researchers had built careful, peer-reviewed models predicting what the crossing itself should look like and what awaited on the far side. The overwhelming consensus of that modeling work predicted a relatively gradual, gentle transition. The solar wind should thin out slowly as it lost strength, the interstellar medium should become gradually more detectable as its influence grew, and the whole process should resemble a smooth blending at the edges rather than any kind of sharp, dramatic boundary. That is not remotely what Voyager 1 actually measured when it made the crossing on August 25, 2012. At the heliopause itself, the particles Voyager 1 detected were not thinning out calmly the way the models predicted. They were moving at speeds approaching a significant fraction of the speed of light, colliding with each other at energy levels that generated temperatures researchers have described as reaching approximately 30,000 degrees Celsius, not inside a star, not anywhere near one, but at the outer boundary of our own solar system, in a region every existing model had described as relatively cold and sparse. Some researchers studying this data have described the region using language that sounds almost contradictory given the emptiness of space itself. A wall of intensely energetic charged particles, forming a genuine physical barrier at the edge of everything our solar system contains. This wasn't a smooth, gradual handoff between two environments. It was something closer to a violent transition zone that none of the careful modeling work done in the preceding decades had adequately predicted. And then came the second surprise, arguably even more significant to physicists than the temperature discrepancy, because it touched on something more fundamental than a single measurement. For decades, one of the foundational predictions about the structure of the heliopause involved magnetic fields. Scientists expected that crossing this boundary would reveal two completely separate, distinct magnetic environments. The sun's own magnetic field on the inside, carried outward through space by the solar wind, and the entirely separate magnetic field of the wider galaxy on the outside, with the two meeting at a clean, sharp boundary where their very different orientations would make the transition obvious and unambiguous. Voyager 1. It was found something categorically different from that expectation. The magnetic fields measured on both sides of the heliopause were, in ways no existing theoretical model had predicted, connected. The sun's magnetic field lines, carried outward and compressed at the boundary by the pressure of the surrounding solar wind, were interacting directly with the galactic magnetic field beyond it, through a physical process called magnetic reconnection, in which field lines originating from entirely different sources rearrange themselves and release energy in the process. Think carefully about what that actually means, because it represents a genuine, fundamental shift in how scientists understand our solar system's relationship to the rest of the galaxy. Our solar system and the wider galactic environment surrounding it are not magnetically separate, isolated systems, the way researchers had assumed for decades. They are, at this specific boundary, magnetically linked, connected by an active zone, where energy is being continuously exchanged between our home and the wider cosmos beyond it, in ways that every model built before Voyager or Enterprise or Perdue's actually crossed that boundary had simply failed to account for. This is not a minor footnote buried in an obscure technical paper. It's a foundational correction to how physicists understand the basic structural relationship between our solar system and the galaxy it's embedded in. If that relationship is genuinely more dynamic, more energetically connected, and more actively exchanging material and energy than existing models described, then scientists' broader understanding of how the heliosphere, the sun's protective bubble encompassing our entire solar system, actually behaves and protects everything within it, over long geological timescales needs to be seriously reconsidered from first principles, rather than simply adjusted at the margins. It's worth pausing here to address something directly and honestly, because it's exactly the kind of detail that separates a credible account of this discovery from an exaggerated one. None of what Voyager 1 measured at the heliopause suggests any kind of imminent danger to Earth, and no credible researcher studying this data has claimed otherwise. What it does suggest is that our understanding of the mechanisms protecting our solar system from the harsher radiation environment of the wider galaxy has been built on assumptions that turned out to be measurably incomplete, and that genuinely understanding the long-term behavior of that protective boundary now requires accounting for physical processes, extreme particle temperatures, and active magnetic reconnection that weren't part of the original theoretical picture at all. This wasn't the only unexpected discovery Voyager 1 delivered around the same period, and understanding the broader context helps explain just how genuinely disruptive this data was to existing assumptions across multiple areas of heliophysics simultaneously. Because Voyager 1's own plasma instrument, the tool specifically designed to directly measure solar wind density and confirm the exact moment of the heliopause crossing, had actually been damaged years earlier, back in 1980, during the spacecraft's flyby of Saturn. That meant scientists couldn't rely on a single, clean, direct measurement to confirm the crossing had actually happened. Instead, researchers had to reconstruct the moment using indirect evidence gathered from Voyager 1's other functioning instruments, tracking a sudden spike in cosmic rays arriving from outside the solar system, alongside a corresponding drop in particles native to the solar system itself, a process that took an entire additional year of careful analysis before NASA felt confident enough to officially confirm in 2013 that the historic crossing had actually occurred back in August of 2012. That delay, and the indirect nature of the confirmation itself, added an extra layer of scientific caution to the entire announcement, precisely because researchers understood how significant and how surprising the underlying data actually was, and wanted to be certain before making the claim publicly. 6 years later, when Voyager 1's twin spacecraft, Voyager 2, made its own independent crossing of the heliopause in November 2018, its own plasma instrument was still fully functional, giving scientists their first clean, unambiguous, real-time confirmation of a heliopause crossing using direct measurement rather than indirect reconstruction. And when researchers compared Voyager 2's direct measurements to Voyager 1's earlier, harder-won data, they found additional confirmation of just how genuinely strange this boundary actually is. Voyager 2 measured its own version of unexpectedly high temperatures just outside the heliopause, its own version of a magnetic field structure that didn't match the clean, separated model scientists had originally expected, and evidence that the heliosphere itself isn't a simple, symmetrical, sealed bubble at all, but something closer to a leaky vessel, with material from inside our solar system found slipping out into true interstellar space more than 100 million miles beyond the boundary itself. Taken together, this entire body of evidence, gathered patiently across nearly a decade by two aging spacecraft that were only ever originally designed to survive a 5-year tour past Jupiter and Saturn, represents one of the most significant course corrections in modern heliophysics. Scientists spent decades building careful, mathematically rigorous models of what the true edge of our solar system should look like. Models built entirely from indirect observation, using telescopes and theoretical extrapolation from the safety of a solar system nobody had ever actually left before. And then, when an actual physical instrument finally crossed that boundary and measured the real conditions directly, it found extreme particle temperatures nobody predicted, a fundamentally connected magnetic environment nobody expected, and a porous, leaking boundary structure that broke the clean, symmetrical picture nearly every existing model had assumed to be true. NASA never designed Voyager 1's mission around finding any of this. Its original goals were modest: photograph Jupiter and Saturn, gather what data it could, and complete its work within about 5 years. Instead, it kept traveling for decades beyond anyone's original expectations. And when it finally reached a boundary no spacecraft had ever crossed before, it delivered a set of findings that forced physicists to fundamentally rethink assumptions that had stood essentially unchallenged for the better part of half a century. That is not manufactured drama for the sake of a dramatic headline. That is the honest, well-documented, peer-reviewed record of what actually happened when humanity's furthest-reaching spacecraft finally measured the true edge of our solar system directly, instead of merely theorizing about it from a distance. If this kind of story is what you come here for, one grounded in real data instead of invention. Hit subscribe and turn on notifications, because there's a lot more of the real universe left to explore. Drop a comment telling me which of these findings genuinely surprised you the most, the extreme temperatures or the connected magnetic fields, and share this with someone who still thinks we already understood exactly where our solar system ends.